Alrighty, welcome, good morning everyone. I'm so glad you were able to make it. I know I wouldn't have been. This is a little too early for me, but nonetheless, we're gonna get really deep into some technicals. That's the best way to start the day. Hello, Sunny. So, Casper, Plasma, and Sharding, these are like the three pillars of Ethereum in 2018. I talk a lot about Casper, or at least I did last year, and so I'm going to assume everyone knows Casper like the back of their hand. But we're going to get into minimum viable plasma. So hopefully I've given this section of the talk a number of times, but I think it's good. And this time I'm refining it. So this is going to be the best minimum viable plasma overview. So number one, minimum viable plasma, it's about scalability, right? We're trying to scale the blockchain, but it's not scalability at all costs. It's scalability while maintaining decentralization. So we want to make sure that the security of the plasma chain, it is as secure as the root chain, essentially. And if you have a plasma chain that is not as secure as the root chain, then it's not really a plasma chain. And these are the kinds of guarantees that we want to make sure. Tokens cannot be double spent, and so the Plasma MVP, I should say, is a token transfer blockchain. So it's based UTXO, super simple stuff, and it has the normal security guarantees of a token transfer blockchain. Let me actually start my timer so I know how long we're going. Okay. So, tokens can always be redeemed on the main chain. This is the key to the security property that Plasma provides. If the Plasma chain goes bad, then you can always pull your coins off and bring them onto the main chain. So, Plasma exits. This is actually how you pull the coins off of the main chain. And off of the Plasma chain. And it's the key mechanism which secures Plasma. And the MVP is designed for just simple token transfers, just transacting any ERC20 token or Ether. But it can also be designed for ERC721, general state transitions, et cetera. So this is actually an active area of research, and there are many active areas of research that are going on in parallel. And so the cool thing about Plasma is it's not a protocol given to the people. It's essentially a design pattern that is been starting to be explored, and anyone can contribute their own, make their own Plasma implementation. But if you do make your own Plasma implementation, make sure that the security is actually secure. Make sure that it actually does require the root chain to be compromised for your Plasma chain to be compromised. If you have your Plasma chain, if it is less secure than the root chain, or significantly less secure than the root chain, then it doesn't really follow the kind of guiding principles of Plasma. We are implementing Plasma, and we have a call once every 2 weeks, and it's super exciting, so please check out the YouTube channel. Boom. So here is an overview of MVP. We've got on the left, we've got the miners. In the middle, we've got the Plasma operator, and on the right, we have the Plasma chain. So the Plasma chain is actually Plasma contract is deployed on the main chain, and that manages it essentially secures the Plasma blocks, and those blocks actually exist in the Plasma operator's database. So we're going to go over a few kind of normal functions of a Plasma chain. Basically, the operator is going to create a block. A new user is going to come in and start transacting. Then we're going to have the new user try to steal some coins, basically double spend in some ways, and we're going to destroy that. We're going to make sure that doesn't happen. And the operator is also going to create an invalid block, and the users are going to exit. So this is what I was saying about the root chain security. We want to make sure that the Plasma chain is as secure or close to as secure as the root chain. And that is why we can actually have a single Plasma operator, because it is a constrained authority. This is a proof of authority network at first. However, it is a constrained authority. So the Plasma operator is going to create a Plasma block. This Plasma block is contained in the Plasma operator's fancy database, and it's going to send a transaction which contains the Merkle root of the transactions and the state to the main chain. And the miner is going to receive it and mine a block. And so that basically makes the Plasma chain block go from light gray, where it's not confirmed, to confirmed, once it's been included in the Ethereum main chain. So Sam is going to come over, and we're going to have Sam do some transactions. So Sam's going to deposit some ETH. That immediately creates a block on the main chain. That block is going to say, OK, Sam now has this balance, and it automatically confirms, because there's no real cost. Like, if you were to think about what's actually happening, you're sending a transaction on the main Ethereum network, and the main Ethereum network is just immediately adding like some data to the Plasma contract. So now the Plasma operator is like forced to update their state to sync with the main chain. So Sam is going to now start watching the main chain for misbehavior. And Alice will come in and do the same. So Sam is going to send a bunch of tokens to Alice. So sends 2,500 PETH. That, just because, you know, we now have 1,000 transactions per second. Oh, great, we can scale. And it'll create a block with all of those transactions. And note that the block has not been confirmed. The block will then be submitted into the main chain, and the miner will mine the block. Now, you will notice that the balances have not yet been updated. This is because there is a confirmation mechanism. We're actually going to get into potential ways to remove the confirmation mechanism later on. However, this is in the Plasma MVP spec, you still have it. So Sam is going to notice the two chains, the Plasma chain and the root chain, see that the transaction was included, and then sign a message and send it to Alice saying, OK, I actually do acknowledge the fact that my transaction was in the main chain. And at that moment, Alice can actually spend those coins. Great. So Sam is now going to try to exit with coins that Sam no longer has, because Sam sent them to Alice. So Sam submits an exit transaction onto the main chain. So remember, the main chain is really, you know, the final arbiter of all the different things. And that's what keeps the Plasma operator in line. That's what keeps each user in line. Now, the exit transaction is going to come in, but the exit will have this challenge period. And the challenge period says, OK, if your exit is invalid, then, you know, I'm accepting any transaction from anyone to challenge this. And anyone who challenges it successfully is going to receive a security deposit bond. So Alice will notice that this exit has been included in the main chain, and immediately say, OK, I'm going to try to challenge this exit. And in fact, anyone can notice that an invalid exit has occurred and challenge it. And so the incentive is, OK, I'm going to submit an exit. It's going to come with a bond or basically a bounty for anyone who challenges me, and that will pay for the person's time to challenge. So this is a really nice thing. Basically, it's like if you were trying to steal something, and as you stole things, you gave a bounty for, you know, catching you. It's really a nice incentive. So sends the challenge before the challenge period ends, and with basically the Merkle proof of the transaction tree and the state tree. And the contract evaluates that, checks to see that it's invalid, and pays Alice's security deposit. So it cancels Sam's exit. Great. So super exciting. Attack failed. 1 out of 2. Now, the next one, operator is going to create an invalid block. This is a little bit scarier. Because the operator is able to create new blocks, that allows an operator to essentially create a block which prints a bunch of money for itself. Now, the issue here is the Plasma operator now has 999 PETH. PETH is, by the way, just the Plasma ETH. Sam has 2.5, Alice has 3.5. This is a little bit scary because the smart contract itself doesn't have 999 ETH. So the Plasma operator is going to send a transaction to the root chain. The root chain is going to then mine it, and we're in trouble. We're in trouble. The root chain now thinks that Plasma operator has this amount of ETH. So the clients notice this bad behavior, and they say, OK, I actually don't want to. I'm not going to be in this chain anymore. I'm going to exit before my money gets stolen. So the exit comes in, and the Plasma operator submits an exit as well. So this is scary because the Plasma operator, if they were to be able to exit, would be able to steal, you know, basically all of the PETH, all the ETH that is now locked up in the Ethereum smart contract. So exits are mined, and the interesting thing is they are processed based on transaction ordering. So the idea is when you send a transaction, it's going to be included in one of these blocks, and we're going to say, OK, the last person who sent a transaction for this coin is going to be the one who gets their coins back, unless there's a challenge. So the exits for the plasma operator are going to be in a later block than the exits for Sam and Alice, but we'll see how that works. So on the sides you have the ones, right? So we're going to go up through all of the blocks and see, when do we return funds. So block 1, no funds returned. Block 2, no funds returned. Block 3. And then block 4, we now have that transaction that Sam sent to Alice. And so we're actually going to start sending ETH back to Sam and Alice. So Sam gets her 2.5 ETH, and Alice gets her 3.5 ETH. Now, funny thing, Plasma contract has no ETH left. Lol, pwned. So we just took this Plasma operator out. Now, this is something new for this overview. This is a reenactment that maybe will make a little bit more intuitive sense because there are more cats. So this is the Plasma operator attacking the Plasma chain, and this is your users. And the users are like, F this, I'm meowt. And they send exit transactions. So they go, dun, 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 exiting the Plasma chain. Woo! Boom! Pwned easy. So we just took them out. Oh, man, that's so much fun. Exit failed. Go Plasma, right? So it's exciting because Plasma allows us to scale up to many transactions per second, but we still get the really strong security guarantees that are based on this crypto economic incentive game that is being played with Casper and proof of work that is securing the mainnet Ethereum. So we have the same kind of, or very similar security guarantees, but we get this nice transactions per second boost. Now, there are other Plasma chains, Plasma Cash. So Vitalik has just released or talked about it yesterday. Vitalik and I came up with this just like a few days ago, and it's super exciting. And so Lil Wayne is checking out the Plasma Cash. Super fun. I love Lil Wayne. Anyway, so minimal client. So there are a couple nice things about Plasma Cash. There are pros and cons for all of these Plasma designs. Remember, the important part of this is it's a design family. It's a family of designs. Now, Plasma Cash, minimum client validation. So clients are watching for misbehavior. In the previous Plasma chain, the clients would have to download all of the blocks and validate all of the state transitions. Because you could, the Plasma operator could at any point create out of thin air a bunch of tokens that increased the balance really high and then just exited with everyone's coins. However, in Plasma Cash, the exciting thing is we give a serial number to individual tokens. Now, what does this actually do? This means that right before we were submitting this root hash, and we're still submitting a root hash. This is just, we're technically 2 root hashes, but I won't go into the details. But the important thing is that now Alice can just check for coins that are relevant to Alice, or Sam can check for coins that are relevant to Sam. And that means that if you hold 10 coins in your wallet or something like this, then you're only verifying the branches of the Merkle tree that are related to you. So this Merkle tree can get really huge, right? You can scale up this Plasma operator without actually having to scale up the user's computers for verification as well. And so this is important because if we were to scale up the Plasma operator without doing this kind of like sharded validation, then we would lose our security guarantees around being able to detect when some operator was malicious and exit the chain in time. So it's really about constraining the operator while still preserving security guarantees. So let's take a look at this Merkle tree. Now, I really want to give more talks explaining Merkle trees because they're so incredibly useful for designing all of these things, because you can prove inclusion and you can prove exclusion. So you publish this one hash, right? And then you can prove that all of these things exist in that hash, or that something else does not exist in this tree. Sorry, I should say. So the way that this kind of works is you have these two addresses. They get hashed together. Well, before I say that, I forgot to mention that the IDs for each coin is based on, at least in this kind of simple version, the IDs for each coin is based on just the index of the token in the Merkle tree. So you basically have coin 0 is owned by Sam and coin 5 is owned by Althea. And so what we actually do is we have these hashes, and they make sure you hash together the Sam's address and Alice's address, and you get, whatever's up here. And then you can hash together these two, and you get what's up here. And so a hash is just, you take some data, it produces a unique output for, like a one-to-one mapping, essentially. And so you get this nice property where, because this and this can only equal this, and because this and this can only equal this, then this and this can only equal that, and this and this can only equal that. So you can actually, just by saying, okay, do I want to see if Sam's address is in this chain, you can just verify, okay, does this and this hash together to that? Does this and this hash together to that? Does this and this hash together to that? Okay, it checks out. That's, included in the Merkle tree. And so we can also say, okay, let's, someone wanted to see if I actually owned coin 0 instead of Alice. Well, you can hash these two together, and you basically immediately realize that doing this stuff gives you an alternate root hash. So just changing one element on these in the leafs allows you to see that was not included. And so this is what we're actually submitting to the blockchain, and this is where we get our we get to compress a lot of information. And so this is useful for all sorts of cryptoeconomic protocols and plasma chains and just everything. It's an amazing construction. So, great. Sam is going to, and this is kind of shows you that you only care about your coins, right? Sam has, if you receive a coin, you're going to check the Merkle tree, and you're going to say, okay, is that coin valid on this Merkle tree? Am I allowed to have it? And so remember, you're only checking one part of the tree. So you can actually, with this, start scaling up the plasma operator. So the plasma operator is even big. Now the plasma operator is really big. So not everyone can then create a new block, because not everyone can verify all thousands and thousands of transactions that are going on, but everyone can verify their portion of the Merkle tree. And because you can verify your portion of the Merkle tree, we can scale up block proposal, aka who's able to change the state, without losing the security guarantees of, if the change is incorrect, then users are able to leave or challenge it. So that's really important. And so this is a really nice thing. Another thing is we get to remove confirmations. So that means that before we were sending transactions, and Sam had to watch the main chain to see if it was included and send a confirmation to Alice. Well, now we don't actually have to do that. We can just send transactions to the main chain, it gets mined, and the balances are immediately updated. So this is really nice. It's just a UX big gain. And the last little thing is mass exit mitigation. Basically, because you have to exit coins coin by coin, it means that you don't actually have the ability to kind of print a new change the balance of your plasma operator and then send one exit to take all of the coins. Instead, you can just instead the plasma operator would have to send exits to many different coins, which means that users have a chance to kind of battle it out, and they can challenge those exits. So it basically the kind of result of all this is that users are not in a mad dash to get their coins out if there is an invalid state transition. So that's great. Cool. So there's not, this is not like a panacea. There's always trade-offs, but we're working on kind of like addressing these trade-offs, and you should work on addressing these trade-offs too, because you should be designing your own plasma chains, because they're a lot of fun. And so some issues are like the indivisibility of tokens is hard to get around. So essentially, if we're limited by sending individual tokens, maybe if the smaller the denomination, the kind of less worth it is to print a new token on the main chain and bring it onto the plasma chain. So this is something that we're addressing with potentially splitting the tokens into smaller pieces, or probabilistic payments. So essentially that's saying, okay, I'm going to pay you 50 cents by saying I'll give you $1 every other time. This is not quite perfect, but it can work for some micropayments. So and clearly there's still no state transition. So there's still like a lot of different areas in Plasma that we can research and work on and get better. Like state transitions would be awesome if we can, there are just many, many designs that we haven't explored. And so please join the Plasma, watch the Plasma call and think about your own Plasma chains and learn Merkle trees. So contribute. It's great. There's a lot of research. Fun. So this is like an important design pattern, right? The whole point of all this Plasma stuff is that we're trying to scale blockchains while not losing the kind of decentralization that we get from blockchains. The reason why we're all here in the first place, it's this whole new design pattern, this new paradigm kind of like mind shift that's going on where we realize that computer programs are powerful and we want to make sure that the people who control that power or the systems that control that power are well balanced and not exploitable. So what we're trying to do is we're trying to constrain actors that are key participants that could potentially mess up the system. So essentially, why are we using deposits? Well, it gives us large incentives to punish validators. So it constrains them, and then if we have any problems with them, we punish them. So this is just like an example of like, this is the thought process that creates these new crypto economic protocols. It's constraints. And so another thing is this is where trust is really established, because by limiting the potential actions of actors, we are able to say, okay, I don't know who's playing this game. I don't know who's participating. I don't know them personally. In other words, I haven't established some kind of social reputation or something with them, but I know that they are constrained in what they can do to me, or I have some recourse if they ever do something wrong. And so because I know the rules of the game, I'm much more comfortable playing it. And so this is critical. And so when you're designing these protocols, you need to impose costs for bad behavior. And that is kind of, this is the crux. We are constraining central authority when we build these crypto economic protocols. So we want in Plasma to store minimal information on the main chain. We want to make sure that we don't actually compute every state transition directly on the main chain. That's where our security, where our speed benefits come in. And the Plasma, it basically allows you to not store so much intermediary state. In other words, if I send you transactions and you send me transactions and we go back and forth a bunch of times, the only time that the main chain actually cares is when we exit. Right, we can still be transacting amongst ourselves, and then only when we exit does the main chain care. And so that's where we get our speed benefit. And so this threat of recourse, even though we have what seems like a central operator, right? That Plasma operator was a key actor that has special rights in that they were able to produce blocks. But even so, they were constrained in what they can do. And that allows us, once again, to trust the chain. Now, you can actually break that up and maybe make the central actor a proof of stake, validators that are validating availability, which is part of some designs that we're thinking of now and that you should be thinking of as well. But it even works in the context of a completely centralized, proof of authority operator. So, exciting. So there's some other constructions. Once again, exchanges, arbitrary state transitions, even more scaling techniques. This is really important. And something else that's important is the base level sharding for higher throughput. So we can process more transactions per second if we scale up the main chain. So that brings us to sharding. So we gotta learn all of Ethereum in 35 minutes. So sharding, phase 0 and phase 1. This is where we're kind of where we are now for implementing sharding. And we have sharded clients, by the way, that are in the works. You should check out github.com/ethereum/sharding. So these clients do not even require hard fork. But let's get into what sharding really is in the first place. So this is what we have right now. We have a bunch of computers that are running the blockchain, and they're processing every single transaction, right? And so now, one way we could scale a blockchain, and so one way people are scaling a blockchain, is by just making it so that you process more transactions per second, right? And that just means that you have a beefier computer that's processing more transactions per second, right? Right now, we process 15 transactions per second. That's only because we have a particular constraint on what kinds of computers we want to run Ethereum. Now, what we could do is we could say, okay, only beefier computers can run Ethereum now. And now we're processing 100 transactions per second, 150, whatever. But that means that the number of people who are actually able to verify the state transitions goes down, right? The whole point of us doing that plasma cache thing was so we could make it so that we scale up the blockchain without having to verify, having the clients have beefy computers to verify. This is the same concept. And then, we could scale it even larger and just have one big computer, quantum computer, that's doing all the blockchain for us. But the problem is this doesn't at all constrain the central authority. We're kind of beholden. We can't even verify whether or not things are going right. And so this is like, okay, yes, you can scale a blockchain, but can you scale a blockchain and maintain the whole reason why we're here, which is constraints on authority, decentralization, incentive alignment, all that stuff. So instead what we're doing is we are using sharding to essentially take all these little computers, put them together, and create one fancy big computer that is kind of the sum total of all of those computers running in the network. So we design a mechanism or a number of mechanisms which then, when combined, when all these computers combine, create this one pretty fast machine. It's a little bit crazy to think about, and it's hard to build, but everyone can do it, and it's actually very possible to do, and we're already getting there. But we can always get help. So please do contribute. Sharding phase 0. So this is the kind of very first sharding move, and this is just actually all it does is first it doesn't require a hard fork. Instead, we just deploy a contract on the main chain, a validator manager contract, and that is essentially that takes some validators and you put up some stake, and then you can validate the kind of sharded network. But the interesting thing is, it has a set of validators, it has Ethereum shards, but it's only data availability. This is not like state transition. So we're basically only saying, okay, data is available. Now, if you actually, as you design these protocols, you realize how hard data availability is. Like, knowing that data is going to be there is required for being able to prove that something went wrong. If you don't know what is actually going on, then you can't prove that something went wrong. So we're solving this one first. But then phase 1, which should shortly follow, we're actually going to be including the Ethereum upgrades for like eWASM and account abstraction and all the kind of fancy new Ethereum tech that's in the works, so that your new clients on these shards are going to be super fast and super easy to program. Now there are 3 main actors. There's kind of 4, but 3. I'll just call it 3. You have users, you have block proposers, and you have validators. Now, the way that this works is the users are going to be sending transactions to the block proposers. The block proposers are going to be composing a bunch of transactions, bundling them together, and creating a block or a collation on a particular shard. These transactions, by the way, specify the shard ID. And then those blocks are going to be sent to the validators, or the collations. The collation is the name of a block on a shard. So the collations will be sent to the validators. And the validators, what they will do is they'll just say, okay, this collation exists. And so there's going to be an interesting relationship where users pay block proposers or collation proposers, and block proposers pay validators. And so essentially what is cool about this is you can actually have it so that the block proposers they are on a particular shard, keeping track of this shard, and they can have interesting rules for how they collect transactions. Maybe they are a block proposer for a particular dApp, and that dApp says, okay, we want all of our transactions to be included first, and we want every single one of them because we want our users to have a good experience. That means that they can collect a bunch of transactions, filter them by only their dApp, propose the whole bunch of transactions to the validators, and pay the validators enough that they are included in the main chain. So this is actually really natural. Once you start thinking in this way, like when you separate data availability from state transitions, it really gets a lot easier to think about these protocols. So what are some terminology? We've got validators who are randomly sampled to create collations. So remember, these are like the blocks on the shards. And the reason why we're randomly sampling them is we don't want validators to be able to particularly target one shard, because that would mean that if you were able to target one shard, then you could like 51% attack one piece of the network. But instead, what we want to do is we want to randomly sample from these validators, so that you would to attack the network, you'd have to have a majority stake in all of the validators. And we're going to create these collations And then the validators are going to check that they exist and submit the headers to the main chain. And so this is just like what a header looks like. But I don't think we have time to go into. So now, the other thing is there are these periods. Periods, yet another term, I'm sorry. It's basically 5 blocks right now. It can change. The idea is that it's the number of blocks it takes for every shard to have inputted a collation header into the main chain. So once per period, every shard should be able to update. And so what this means is the validators are able to, we have this thing called look-ahead periods. And look-ahead periods say, OK, what am I going to be validating in the future 4 periods ahead? And so that gives you like 20 blocks to say, OK, I'm going to need to validate this shard, so let me download block proposals and things relevant to that particular shard as a validator, so I can then contribute to it. So this is how we get give our validators enough time to get ready to produce a new block. Great. So the validators are just verifying block availability. Once again, super cool stuff. So here's a little example of what this really means. So each period, right? These circles are periods. The squares are blocks. Each period is 5 blocks. And what we're going to do is we're going to do this nice little thing where we first look ahead, then clients are going to submit some transactions, then the block proposers are going to create a collation, then we're going to have the validators download and submit the block or the collation, and then we'll have a little bit of an attack and we'll mitigate it. So this should be exciting. The last two are some little, this is an attack and this is a mitigation. So first, the look-ahead periods. So here we have the 4 look-ahead periods. These haven't happened yet. We're currently on this shard. But we're going to be able to see, the validators will be able to compute which shard they're going to be validating. So this guy's validating shard 1, this guy's validating shard 2, etc. And so you see, we're just like randomly sampling from these validator sets. And so no validator is going to have too much power over one shard. That's where this kind of like decentralization, this security guarantee around particular shards having the same security as the full validator set. So boom, we've got this look-ahead period. Now what we're going to do is the client is going to submit some transactions. Great. So they submit, whoops, that was really fast. They just submit a transaction to the transaction pool. It tells what shard you want to talk to. And so the block proposers are going to come in and pull from the transaction pool and create a collation. Now the validators, they're going to take these collation proposals and they're going to just submit some to the main chain. So they pulled it into they pulled them in, and now there's oh, whoopsies. So first, before they know what to build on, excuse me, they're going to verify that the data is available, because there's in the validator manager contract, they only want to build on available blocks, because that's the only blocks that they get rewards on. So they're just going to go 1, 2, 3, they verify as far back as they would like, and then they choose a head and they build on top of it. So submit some collation headers to the main chain, and boom, now we have updated all of our shards at the same time. So you can kind of think each one of these validators is running a pretty simple protocol. It's going to be running on a laptop. Each one of these block proposers or collation proposers are running on a laptop. Users are running on a laptop. But still, we're able to shard, and we're able to get many, many more transactions per second, because not everyone is validating everything. So now we're going to say the evil validator is going to come in and submit a invalid block. And so we'll see how that works. Basically, we follow the same format that we did before, downloading some block proposals and submitting to the main chain. The evil validator is going to propose and create an invalid block, so no one's able to download this thing. What are we going to do? Well, we're going to say, OK, I am a new validator. I am not evil. I'm this guy. I'm going to instead build on I'm going to check the history, and I'm going to say, OK, that's unavailable. I wasn't able to download it. This is available, and I'm going to keep going back. That's available as well. I'm going to choose this as my head instead of the one that I couldn't download, and build on that one. So now we have this way for validators to, just circumvent a unavailable block. And this is all managed in the Validator Manager smart contract. So super exciting. We're able to get this kind of scaling, able to prove availability, and mitigate these kinds of attacks if they ever do come up. Cool. So attack failed. Go sharding. So amazing. We now have this Casper, Plasma, Sharding, I wish I went over Casper, but you know, there are a lot of videos online. But we have all these things. Casper giving the security of the main chain, you know, making sure that validators that misbehave are going to be penalized. And Plasma, a design principle that allows developers, even on the current Ethereum, without any, you know, sharding, to get a lot of transactions per second through like really, you know, good, well-designed protocols. And then sharding, where the core chain is going to be able to be moving, you know, much faster. And this is actually, you know, sooner rather than later. Once again, shout out to github.com/Ethereum/sharding. So, with Casper, sharding, and Plasma, we can scale to the moon. This is you know, just to, I don't know, give an idea of like where the validators, we have this one set of validators, and they're super duper constrained. They're super, you know, secure. We know, we trust them because we have this economic proof that says, okay, if the validators misbehave, they'll get punished, and there's these consequences for doing things that we don't want. And then we're going to also have the ability for the validators to have that security split up onto multiple different shards, so that we can get transactions per second, high throughput, and each one of these can be run on a laptop, so we don't lose that decentralization verification stuff. And then we have the ability for each one of these shards to contain tons and tons of applications, you know, and many of these may be Plasma applications. This is kind of exciting stuff. As long as you design your application well, you can probably fit it on, you know, I mean, if you have a perfect design, you could even fit it on today's blockchain. But later on, it'll be easy to get, you know, really high throughput. So this is something that came up during dinner yesterday. Shout out to all the people at dinner. Where it was like Web 1.0, we have these like static web pages, and everyone's serving static web pages to each other. So it's kind of like decentralized in a way. And then we have Web 2.0, where we have this like social media and these big you know, tech giants that pop up. And now we're submitting comments and posting things, and we're giving our data to these central authorities. But now with Web 3.0, what we're doing is we're realizing that giving all of our information and you know, having so much control over where we are going, where we are going is actually dangerous. And so we need to be able to design our applications so that they actually constrain central authorities, baked into the protocol itself. And so that's kind of like what we're doing. And that's why it's so important that we make sure that our, you know, Plasma chains have the same security as the root chain, or that, you know, the validators, everyone is able to validate a chain, no matter your hardware requirements, except for, you know, like you just need a laptop, etc. So this is exciting, and we need to, you know, let's do it. So part of this is that we all need to do it together. So just like everyone needs to be able to validate a main chain, everyone needs to be able to participate in the creation of this new internet. And my personal idea for the best way for this to actually happen is if we have, whenever I design a crypto economic protocol, I'm like, okay, we need a lot of stakeholders with different interests so they all balance each other out. But just like that, we need to protocol design our protocol designing. And so that means that people who are like writing these protocols, like myself and, you know, many people in the audience, they need to be from a diverse set of backgrounds. They need to be a diverse stakeholder group from different communities. And so it is vital for us to actually like achieve this decentralization of power, for us to also welcome in, you know, new ideas, new people from different communities. So if you are, you know, a newcomer to the space, it is so critical. Like, you are like, what is going to save this stuff? Because I know that if it's just, you know, if it's just us, basically, if it's just a small, you know, small group of people from a very particular background, we're not going to build a future that is equitable and really decentralized. It's just going to be, you know, the same old, same old. So let's, you know, continue this like open software, free software movement. Let's, you know, welcome each other. Let's be nice to each other. Spread the love. You know, this is some knowledge sharing right here. Good stuff. Fun, happy, good feels. Good feels for all. So ETH research. Good feels. This is, you know, a lot of really cool stuff is going on. So definitely read. This is where we like post a lot of research ideas, and, you know, take a look. And we want to be as inclusive as possible and open as possible. So this is where we actually talk about our ideas. So that's a Doge. Sorry, I really like that. That was fun. This little Quiet. Anyway, so that's basically it. Thank you. Right in the middle, dead center.
Thank you for your presentation. I had a question about the plasma aspect and the second attack you discussed, the one with the funny cat at the end, about the plasma chain authority trying to do an exit. And if I remember correctly, what you said is that this is prevented by the fact that the user can do an exit and it's executed in the reverse order, so they exit first. Yep. So my question is, what happens if the operators create a new identity, let's call it Dave, with a lot of money, that exits after Alice and Sam? And so is there an assumption that the last exit will be a legitimate one? Because I think attackers can always spam exits later.
Fantastic question. So that is exactly right. So the idea is users are going to be watching the chain to make sure that it is a valid chain that they're building on. If a user is to submit a transaction on an invalid chain, then all of these guarantees kind of go out the window, because we are saying, okay, the user is able to make sure that they're not building on a valid chain, and so why would they build on a valid chain? They're just going to exit if they see it's an invalid chain, and that means that their transaction will be ordered, in order. So essentially, everything is going well. Users are submitting transactions. A bad attack happens, and then all the users stop sending new transactions. They say, oh, actually, now I really should not be building on this chain, because the guy would, if I did build on that chain, if I did submit a transaction, then they would be able to exit before me. And so that is absolutely correct. And this kind of, and anyway. I wish I, is there more? Is that it? Huh? We're out of time? Well, thank you so much, everyone. Talk after.